Good afternoon, friends in India or Asian continents. Good morning to the friends from Europe, particularly the speaker. He is from now Poland, where it is morning. And I'm very happy again to welcome you all on behalf of my team to this webinar series. We have been very fortunate to have very nice speakers. And today we got confirmation from Professor Hideo Ono. He will be giving a talk sometime in October. And yeah, so there are many eminent speakers in the list. You can see the website of our W2S, find more information. So today we have Dr. Bivas Rana. It's my pleasure to introduce him. We know Bivas from very long time, from his student time at SN Bose. And he has done really outstanding work during his PhD and postdocs. I'm really pleased to introduce you, Bivas, to this W2S. So Bivas is now working as an assistant professor in the Department of Nanostructure Physics, Faculty of Physics in Adam Mickiewicz University in Poznan, in Poland. And before that, he was a postdoc at Riken in Japan in the group of Professor Weshi Watani. Also there, he was working as a research scientist for about 2.5 years before moving to Poland. So he was actually with Professor Watani almost for like 5-6 years, isn't it?
7 years.
Yeah, 7 years, so a long time, and did wonderful work there. So he did his PhD under the supervision of Professor Anjan Burma from SN Bose Center for Basic Sciences in Kolkata, with the thesis titled Quasi-Static and Ultra-Fast Magnetization Dynamics in Magnetic Nanostructures. And he did his MSc from IIT Delhi. And his research interests are excitation, manipulation, and directional channeling of spin waves by electric field control magnetic anisotropy to develop all electric field control low power magnetic devices. Also, he focuses studies with perpendicular magnetic anisotropy, Zylonsky-Moria interactions, Rasberger-Stein effect, and other interfacial spin orbit effects, on many other topics, which also involve the time visual magneto-optical microscopy for ultra-fast magnetization dynamics. He has developed many experimental techniques during his PhD and postdocs, and he has got a few projects during his research scientist position at Riken as a principal investigator, and he has published about 40 papers in highly impact journals. So with this very brief introduction, I welcome you, Bivas, to this lecture. Thank you so much for agreeing to give this talk. And we are now about 40 people, and I'm sure it will go on. And I just want to request the participants that during the lecture, we do not take usually questions. If you have any question, please write in the chat window. At the end of the lecture, we will take one by one. Thank you so much. And Bivas, we are looking forward to your lecture. Thank you.
Okay. So you can hear me, right? Clearly.
Yes.
Okay. So thank you, Professor Vedanta, for nice introduction and inviting me to present my research work in this great platform. So basically, today I'll be talking about my research. Basically, I will talk about how the voltage control magnetic anisotropy is kind of electric field induced method can be applied for the operation of spin wave based devices or the magnonic devices. And the research work, experimental research work, which I will be presenting here, was done basically in Riken with Professor Shichika Otani and his group. So here are the collaborators or the contributors of this work. So first, the collaborator is Professor Yasuhiro Fukuma from Kyushu Institute of Technology, Japan. And then some of the experimental part was done in collaboration with Professor Anjan Burman from SN Boston National Center for Basic Sciences, India. And some of the theoretical formulation in this work was given by Professor Gen Tatara and his postdoc, Dr. Colin Asuakosa from Riken, Japan, and also all the magnetic thin films with very nice quality was provided by Hitachi Limited, Japan. So here are the outline of my talk. Basically, I will introduce what is the spin wave, and the concept of the magnonics, and what is the voltage control magnetic anisotropy. Then I will slowly proceed to my research result about the excitation and making reconfigurable nanochannels by voltage control magnetic anisotropy. Then I will show you how these nanochannels can be utilized for making magnonic crystal. Towards the end, I will discuss about the modulation of spin wave frequency and the modulation of damping by voltage control magnetic anisotropy. So at the end, I will briefly discuss about some of the future challenges and the conclusion of my talk. So you are very familiar with this slide. I'm sure you have seen it many times, but still I would like to start with this. So as you know, the electronics, we utilize charge current. That is nothing but the flow of electronic charges, because the spins, they have 2 degrees of freedom. One is a charge, another is spin. So when you send the charge current through a conductor, basically it is not spin polarized, because the spins are randomly oriented. So in total you have charge current, but you do not have any spin current. But the Spintronics basically utilize both the charge current and the spin current. So spin current basically is the flow of a spin angular momentum. So there are 2 methods how you can flow the spin angular momentum. First of all, this angular momentum can be carried by moving the electrons itself. So it can be either spin polarized or pure spin current. So in case of spin polarized current, so number of up spins which is moving in this direction are not equal to the number of down spin which are moving in the opposite direction. That means you have a spin current in total, and on top of that you should have also a charge current. But for pure spin current, number of up spin and down spin are same. That means you have pure spin current but without any charge current. But the spin diffusion length of this conduction electron spin current are limited to hundreds of nanometer in a clean metallic system. So what is the other type of spin current? Well, for that, that is called the spin wave. So basically, in the steady state, the spins in a ferromagnetic material are aligned like this, because they are coupled by very short range exchange interaction and long range dipolar interaction. Now, if we part out some of the spins very locally, and by using let's say temperature or the electric or magnetic field, then the spins started to precede around equilibrium position, and that is governed by Landau-Gilbert equation, which is showing that the time rate of change of magnetization is composed of 2 terms. One is a precisional term that is responsible for the precision of magnetization, and another is phenomenological damping term. Okay, so when this group of spins start to precede, then other spins which are coupled with these spins by exchange and dipolar interaction, they also start to precede. But there is a phase lag, of course, and the phase of this oscillation moves along the wave path. Okay, so this is called the spin wave. So that means the spin wave is basically chargeless flow of information. So the quanta of the spin waves are called magnons. Following this name, a new research field called magnonics is rapidly developing. And one of the advantages of the spin wave is the decay length is it can be up to millimeter in ferromagnetic insulator, for example, YIG. Okay, so that means the spin wave spin current can carry information to a much longer distance as compared to the conduction electron spin current. Okay, now what are the applications of the spin wave? As this is a wave, and we can use the wave property like amplitude, phase, frequency by carrying the information. You can encode the information either in amplitude, phase, or frequency, and it can carry information at a very low power consumption, because it is not associated with any translational motion of any charged particle like electron. So that means the spin wave or magnonics can be one of the most promising candidates for post-CMOS computational technology. Okay, now what are the time scale of this spin wave? Well, this time scale can be varied from a few picosecond to few hundreds of picosecond, with the frequency, corresponding frequency from gigahertz, few gigahertz to few terahertz. And if we calculate the wavelength, that can be from few micrometer down to few nanometer. So this that means the spin wave frequency or the time scale is much faster than the dominant motion, but is much slower than laser-induced ultrafast demagnetization. Well, coming back to the Landau-Lissig-Gilbert equation, if you see this, this is a nonlinear differential equation. And here the effective magnetic field is composed of many terms. So one of the terms is external magnetic field or the Zeeman field. And here these two terms is originated from self-magnetostatic field. Okay, the magnetostatic field created by the magnetization of the system. And this is the fourth term is the anisotropic of the spin system introduced by spin orbit coupling. And the last term is isotropic exchange interaction. That means you can tune the spin wave properties by playing with the not only the magnetic field, I mean amplitude and the direction of the magnetic field, but also the size and shape of the nanomagnets, and also playing with the anisotropy of the system. So there are a lot of scopes you can do. So that is the one of the main advantage of the magnonics. So you can tune the spin wave properties by several means. Okay. So now how to solve this nonlinear differential equation? Well, one can do it by linearizing under the linear approximation of the spin wave. So what is that? Basically, you can write down the space and time, the magnetization as a which is varying as a space and time in terms of saturation magnetization that is constant over time, plus a dynamic component of magnetization. Okay, so here this small m is much smaller than ms. Under this condition, you can write down this m as a combination of several linear spin waves having different k vectors and the frequencies. Okay, and if you put this into this equation, then you can get the solution of the spin wave frequency. So for magnetic thinking is quite complex. I mean, the spin wave frequency, it depends upon many factors. But well, here the H is basically external composed of external magnetic field and the exchange field, where the exchange field is proportional to the square of the wave vector of the spin wave, and the P can be related with the wave vector and dimension of the thickness of the waveguide in this manner. Okay, so this is about the dispersion relation of the spin wave. You can see, so depending upon the direction of the magnetization with respect to the wave vector, the dispersion relation can be different due to the anisotropic nature of the dipolar interaction in the system. So basically, there are three basic spin wave mode we always discuss for our experiment. So that depends upon how the magnetization is oriented with respect to the direction of the spin wave propagation. For example, if both of them are in plane of the film but perpendicular to each other, we call that magnetostatic surface mode. Basically, the spin wave propagates to the surface of the waveguide, and this is the dispersion relation of the spin wave. And if they are parallel to each other, then we call this magnetostatic backward volume mode, because this propagates the overall volume of the waveguide. But and this is the dispersion relation, and the third one is forward volume spin wave. So basically, it happens when the anisotropy, when the magnetization is aligned in the outer plane direction of the field. So this all about the spin wave dispersion relation. Now, if you think about a typical, very simplified structure of a magnonic device, it has a 4 basic components as shown by this schematic diagram. So you must have a waveguide. It's made of either ferromagnet or ferrimagnet or antiferromagnet, and where along which spin wave can propagate. And the second part is the excitation port, where you excite the spin wave. And the third one is a detector, where you detect the spin wave. In between, there are many functional devices for amplifying the spin wave, for sending the spin wave through channel, or to manipulate spin wave properties. For example, it can be frequency, wave vector, or the magnonic band structure. Okay, so all these things can be done by electrically or optically or thermally induced methods. But if we really want to integrate the magnonic devices into future nanostructure technology, so basically we should operate this magnonic device by electrical method. Okay, but again, if we let's say use charge current induced method, which are generally found in the literature, then again that will be a problem, because that will consume a lot of power through the Joule heating. So we want electric field induced method, not the charge current induced method. Okay, because that can only reduce the power consumption of the magnonic device significantly. Okay. Now the question is how the electric field can tune the magnetic property. It's not very easy to tune the magnetic property by the electric field. You know about the multiferroing material, and you are quite familiar, I guess, with this slide also. So in the multiferroing material, in single phase multiferroing material, so the ferromagnetism and the ferroelectric phases coexist. Okay, so then by applying the electric field, you can tune the magnetic property and the vice versa. Alternatively, you can make a heterostructure. For example, you can put a ferromagnet on top of a ferroelectric material, and then if you apply the electric field in ferroelectric material and then induce like electrical polarization, so at the interface, this electric polarization interact with the magnetic moment of this ferromagnetic material, and that's how you can tune the magnetic property of the ferromagnet. So the second option is the ferromagnetic semiconductor. So basically, by applying electric field, so you can change the carrier density in the ferromagnetic semiconductor by using a gate, and then you can change the magnetic moment of the system. That's how you can change the magnetic property by the electric field. And the third option is to put a ferromagnetic film on top of a piezoelectric substrate. So when you apply a electric field across a piezoelectric substrate, it induces strain. It may be compressive or tensile strain, and that is transferred to the adjacent ferromagnetic layer. And through magnetostriction of the ferromagnetic layer, you can tune the magnetic property of the system. But I will not use all these three mechanisms. So for my study, I used another alternative method that is called voltage control magnetic anisotropy. So basically, the system I will be using here is composed of a ultra-thin ferromagnetic film and an oxide layer deposited on top of that. So when you do so, at the interface, what happens, the 3D orbital of this ferromagnet, outer plane 3D orbitals are coupled with the outer plane 2p orbital of the oxide layer. And then a finite amount of electrons is transferred from 3D to 2p orbital. So that means there will be an imbalance in the outer plane, imbalance of the electrons in the outer plane 3D orbital with respect to the in plane 3D orbital. And when you introduce spin orbit coupling in the system, that's how the spin are coupled with the orbital momentum. So then you can induce a finite amount of anisotropy in the spin system. So if the thickness of the ferromagnet is limited to, because this is an interfacial effect, is if the thickness of the ferromagnet is limited to 1 nanometer or so, then the spin are preferred to align out of plane direction. Okay, and this is the source of the perpendicular origin of the perpendicular anisotropy in this heterostructure. Now, when you apply the electric field at this interface by using a gate electrode, so what happens? So basically, the number of the electronic occupation state in the out of plane 3D orbital is changed with respect to the in plane 3D orbital, and that's how this relative change can basically induce some of the change in the anisotropy in the spin system. That's how you can change the anisotropy by electric field. Of course, there are some alternative explanation of this origin of this voltage control magnetic anisotropy. One is spin dependent surface screening. So it is well known that when we apply the electric field at the metal surface, the electric field cannot penetrate more than a monolayer or so. Okay, due to the screening created by the conduction electron. But the situation is different for the ferromagnet, because in the ferromagnet, the spins are polarized. The number of spin is different than the down spin. That's why this polarized spin induce some of the magnetic moment. That's how you can change the total magnetization of the system. And the second explanation is the modulation of Rashba spin orbit coupling by electric field. Basically, theoretician says that there is a Rashba spin orbit coupling which exists at the interface of ferromagnet and oxide layer. When we apply the electric field at the interface, that tunes the spin orbit, Rashba spin orbit coupling, and that's how you can tune the perpendicular anisotropy of the system. So another alternative explanation could be, when you apply the electric field through this dielectric layer, it induces some kind of strain in this dielectric layer, and that strain is transferred to the ferromagnet, and through the magnetostriction, the anisotropy of the ferromagnet is changed. Whatever is the mechanism, so basically we can tune the perpendicular anisotropy in a very fast time scale, because this is not related to any charge movement of the ion, or it doesn't depend upon any chemical reaction. That means you can use this for the operation of the devices in the gigahertz frequency scale. Anyway, so this anisotropy, change of the anisotropy can be written in the simplified manner. It can be written as linearly proportional to the electric field. That is the one of the advantage of this voltage control magnetic anisotropy. But this is not the case for all the heterostructure, because this voltage control magnetic anisotropy coefficient always depends upon the band structure at the Fermi level, and how the relative changes at the band structure occurs under the application of electric field. So that means, so if you change the temperature of the system, or change the annealing temperature, you can observe either linear on the nonlinear variation of the perpendicular anisotropy as a function of gate voltage, because that temperature essentially tunes the lattice, clears the lattice strain, and that's how it can modulate the interfacial properties or the Fermi energy of the system. Also, that means people have shown by theoretical study that if you systematically change the strain, okay, so you can significantly tune the behavior of voltage control magnetic anisotropy in this manner. That means this is the playing with the strain can be a nice way to tune or to formulate, to change the voltage control magnetic anisotropy behavior. Not only that,
I'm sorry to interrupt, but there is some strange noise coming from your computer or your office. So some kind of, like paper sliding or some cluster sound.
Okay, maybe some from other office or something.
Okay, we continue. Thanks.
So, and not only that, this also depends upon the underlayer material, because the crystal structure of the ferromagnet, because this is ultra thin film, strictly depends upon what is the underlayer you are using, and that's how it also affects the interface between the ferromagnet and the oxide layer. So for a normal ferromagnetic oxide layer, for example, cobalt iron boron MgO, this VCMA coefficient can be limited to hundreds of femtojoule per voltmeter. But if you engineer the interface, for example, if you insert or dope heavy metal or light material at the interface, you can efficiently tune or enhance this perpendicular voltage control magnetic anisotropy coefficient up to few hundreds of femtojoule per voltmeter. But for practical application, we need at least this beta value picojoule per voltmeter. So people, researchers are trying to, are working on that, how to enhance this VCMA coefficient.
Bivas, I think it's the microphone which is sliding on your collar. That friction is giving some strange noise. Of your earphone, the microphone probably makes some strange noise.
Is it? Okay. Can we?
Maybe you can remove the microphone, we can try without.
So can you hear me?
Yeah, it's very nice. Now there is no noise. We can continue like this.
Okay, you can hear me, right?
Yes, yes. Thanks.
Okay. Okay. So now I will talk about the application of voltage control magnetic anisotropy. So, people started to apply this voltage control magnetic anisotropy to tune the basic magnetic properties like control of the coercive field or switching the magnetization by applying the gate voltage. Also, I mean, you can control the domain wall motion by tuning the anisotropy by gate voltage. Not only that, people have shown that this VCMA can be a nice tool to annihilate or to create the magnetic skyrmion, which is quite interesting nowadays. Not only that, as I told you, that this can be applied for operating high frequency devices. So people have also shown that, sorry, I cannot change my slide somehow. It's frozen. Just a moment. So probably I think the slides are frozen because somehow. Okay. So now can you see? Hello?
Yes.
Okay. Okay. So basically, one can excite the ferromagnetic resonance, and it can be either linear or nonlinear ferromagnetic resonance by this voltage control magnetic anisotropy. So one of the important property of this VCMA induced ferromagnetic resonance is that so this VCMA torque is linearly proportional to the sine of the elevation of the elevation angle of the magnetization multiplied by the cosine of this elevation angle. That means if the magnetization is aligned either in plane, perfectly either in plane or out of plane direction, not possible to excite the ferromagnetic resonance or even the spin wave in the system. So that is one of the important feature of this voltage control magnetic anisotropy. So now I will talk about my research about the excitation of the spin wave by VCMA. So before going to that result, I want to tell you why we want the spin wave excitation by VCMA. So there are several methods, I mean conventional method how you can excite the spin wave. The first one is by using Oersted field. So you have a coplanar waveguide like this, or it's an antenna like this, and you send the RF current across the antenna that generates specially non-uniform magnetic field like this. Okay, then it at the resonant condition, it couples with the spin wave having the wavelength of the same order of this nonlinearity, and that's how you can generate the spin wave. But the problem with this method is the Oersted field is spatially dispersed. That's why you cannot localize the Oersted field, and you cannot apply this method for nanostructure devices. But another interesting way is to excite the spin wave by spin transfer torque. But again, the problem is that this is charge current based method, so it also consumes a lot of power. So other methods are femtosecond laser induced method, that is quite interesting and very powerful method. But I don't know technologically whether it is possible to technologically implement this technique for future devices or not. And also there are some thermal way to excite the spin wave. And I will talk about how you can detect the spin wave. Basically, I will talk about three methods, which I will be discussing for describing my research results. So first one is the magnet-optical Carr effect. Professor Vedanto's group is actively using this for domain wall, for understanding the domain wall dynamics. So basically, this is a very nice and very sensitive technique to measure the domain wall or the spin wave dynamics. So you send a linearly polarized current, linearly polarized laser beam, and upon the reflection, the plane of polarization is rotated due to the interaction with the magnetization of the system, and the angle of the rotation is proportional to the change of the magnetization. That means the amplitude of the spin wave, and that's how you can measure the spin wave amplitude in a very sensitive manner. And second way is by using below light scattering, that is based on the inelastic scattering of the light. So basically, if you send a CW laser light that interacts with the spin wave, so that inelastically scattered from the propagating spin wave, and then from the due to the scattering, so the frequency and the wave vector both are changed, and then you measure how much frequency and the wave vector is changed by the below light scattering technique, and that's how you can measure the spin wave properties. And the third technique is the electrical technique. So basically, if you consider about the heterostructure made of heavy metal and a ferromagnetic layer on top of that, and you excite the ferromagnetic resonance in here, and that creates the spin current. That is the means of transferring the angular momentum from localized magnetic spin to conduction electron, and by virtue of inverse spinol effect, you can generate or transfer that to the charge current, convert to that charge current, and then you measure the potential drop across this heterostructure, and that's how you can measure the spin wave in the system. And this spin pumping and inverse spinol effect is one of the main sources of the damping in this heterostructure, which I'll be talking shortly. So then, before exciting the spin wave, we tried to see how much the anisotropy field we can modulate by the gate voltage in our system. So basically, the multilayer system we use is based on cobalt iron boron and MgO. Of course, as an underlayer, we have tantalum or tantalum ruthenium tantalum. So then what we measure the ferromagnetic resonance of the system under the application of various gate voltage, so that we can tune the perpendicular anisotropy. And here is the typical signal which we measure. So here we plot inverse spinol effect signal as a function of the magnetic field, bias magnetic field for various applied gate voltage. You can see the resonance field is varying as a function of the gate voltage due to the variation of perpendicular magnetic anisotropy. Then what we do, we plot the frequency as a function of electric field, and then by using Kittel formula, which tells the relation between resonance frequency and the bias magnetic field and the perpendicular anisotropy. Basically, you can extract the value of perpendicular anisotropy for various gate voltage, which we have plotted here. So we systematically measure the variation of perpendicular anisotropy as a function of gate voltage for different values of cobalt iron boron thickness, varying from 2 to 2 nanometer down to 1.6 nanometer. In all the cases, you can see the perpendicular anisotropy is linearly varying or linearly proportional to the gate voltage. So we didn't see any kind of nonlinear behavior of this VCMA in our system. So then I will talk about the excitation of spin wave. So to excite the spin wave, what we did, we shrink the size of the top gate electrode with the dimension of 2 micrometer by 10 micrometer. Then we applied the sinusoidal gate voltage, and that generates the electric field right underneath this gate electrode. And that electric field basically tunes the perpendicular anisotropy, periodically tunes the perpendicular anisotropy. And if it satisfies the resonance condition, then the spin waves are basically excited and that propagates in both directions. For the detection, we use a picosecond laser beam having pulse width around 42 picosecond, and we use the car rotation from the reflected beam of the system. So basically, this car rotation is proportional to the amplitude of the spin wave. And for the measurement of this car rotation, we use a specially designed detector called optical bridge detector, and that is connected to the locking amplifier. So if you see the DC IV characteristic of this junction, you can see when we apply the gate voltage up to plus minus 1.4 volt, okay, the current flowing across the junction is almost zero. Okay, so there is no current across the junction. That means the spin wave which we are exciting is purely excited by electric field induced method, not by charge current induced method. Okay, and here are the typical spin wave signal. So basically, to measure the spin wave signal, we vary the delay between this laser pulse with respect to the RF current by using this electronic delay generator. Okay, and the spin wave signal is sinusoidally varying as a function of this delay time. And then by fitting with the sinusoidal function, we can extract the spin wave amplitude, which is half of this peak to peak, proportional to the half of this peak to peak value. So now, what is the K vector we can excite by this method? Of course, to find out that one, we need to do the Fourier transform of the electric field. So electric field underneath this gate electrode can be expressed by this box function. And if you do the Fourier transform, so you get the sinc function. And the square of the sinc function gives the efficiency of excitation of the spin wave as a function of the wave vector. That means, which shows that as we increase the wave vector, the excitation efficiency is significantly reduced and it becomes almost zero at the K vector, which equals to the 2 pi over the width of this top gate electrode. So if you really want to excite the spin wave with a very short wavelength and with a very high K vector in a very efficient manner, you must shrink the size of the top gate electrode. One of the important features of this VCMA-induced spin wave is that the amplitude of the spin wave is linearly proportional to the gate voltage. It's quite natural because the amplitude of the spin wave in the linear approximation, of course, should be linearly proportional to the magnetic field which you are applying to excite the spin wave. And here we are not directly applying the magnetic field, but we are changing or modulating the perpendicular anisotropy. That means it should be proportional to the change of the anisotropy of the system. And that is essentially proportional to the gate voltage we are applying. And that is the reason we get this kind of linear variation of the amplitude as a function of the gate voltage. One of the most important features of this VCMA, or I would say advantage, is the local excitation. So as I explained that this electric field is strictly confined underneath this gate electrode because the thickness of this oxide layer is way smaller than the width of the top gate electrode. And to see the localized nature of this VCMA-induced spin wave, we try to see how the amplitude of the spin wave varies as a function of the propagation distance. So these blue dots shows the experimental result. So as this is a wave, so it shows a nice exponential decay as a function of the propagation distance. And then we compare this with the antenna induced spin wave. Okay, so basically we send this current through a antenna, and that generates Oersted field, Oersted magnetic field. And here you can see this Oersted field is not confined right underneath this gate electrode. So I mean this conductor. That means the effective excitation area is larger than the width of this this conductor. So then when we measure how the amplitude as function of propagation distance, which is shown by the red dots, you can see the effective decay length is like larger than the voltage induced excitation. Especially first couple of points are not exactly following the exponential decay trend. So that so I can conclude here that this voltage excitation can be more suitable for nanoscale device, because you can really shrink the size of the device. You can localize the excitation area underneath this gate electrode. So here are more characteristic of the spin wave excited by VCMA in this thin film. Basically, the most important point is the decay length, which we measured is roughly around 2 to 1 micrometer, but it decays as we increase the magnetic field. Because if you see the expression of the group velocity, so as we increase the magnetic field, the frequency increases, so group velocity decreases, and the relaxation rate, which is also function of magnetic field, that also increases. So that means the decay length, which is given by this formula, should decrease as we increase the magnetic field. Now, after the excitation of the spin wave, basically you want to send the spin wave to a target position. So you send through a kind of channel. Okay. So how you can do that? So there are various means to do that. So first popular example is geometrical confinement. So you can change the geometry of the waveguide. You can make the geometry according to your wish to send the spin wave. But the problem with this, once you make the geometry, you cannot do anything. You cannot change. So the next way is by using spin wave caustic. So when the spin wave enters from a narrow waveguide to a wider waveguide, basically the spin wave, they do not go in the straight line. Okay, they are bent like this because of the anisotropic nature of the dipole interaction. So just by changing the orientation of the magnetic field, you can steer the direction of the spin wave like this. Okay, the third method is confining the spin wave at the demagnetized area, because at the edge of the waveguide, there are demagnetized area where the effective field are smaller than the effective field at the center. That means if you if you change the frequency of the spin wave, the higher frequency of the spin wave, they are confined at the central area, whereas the lower frequency, they are confined at the edge area. The fourth method is confining the spin wave in the domain wall, because the domain wall creates some kind of potential well where you can basically confine the spin wave, and the domain wall size essentially can be reduced down to a few tens of nanometer. So another interesting way is to control the phase of the spin wave by voltage control magnetic anisotropy. Basically, you have several sources of the spin wave. Okay, then you selectively tune the phase of the spin wave by applying voltage control magnetic anisotropy, and then you interfere the spin wave, and from the interference, it goes in a selected direction. So if you want to change the direction, you just tune the anisotropy of the spin waves systematically. And our proposal is different. So what do you have to do? Basically, if you make a top gate electrode made of gold, and with the dimension essentially smaller than the dimension of the waveguide, then apply the DC gate voltage, you can basically tune the perpendicular anisotropy right underneath this gate electrode, and that makes create some kind of virtual channel in the system, where if you take a line scan across this dotted line, so you can create kind of a potential well where you can confine the spin wave, and this is how we can confine the spin wave by VCMA induced virtual nanochannel. So if you see the dispersion relation of the spin wave where in this system where the spins are aligned in the outer plane direction, basically the frequency can be written as a function of perpendicular anisotropy. So we are basically tuning this perpendicular anisotropy, and let's say you draw the how the frequency varies as a function of k vector. So basically outside of this channel where you are not applying any gate voltage, this is the dispersion relation, and inside the channel the dispersion relation is downshifted because we are applying the gate voltage and we reduce the perpendicular magnetic anisotropy. So then let's say if you want to excite the spin wave, for example at 14.4 gigahertz frequency, you can only excite the spin wave inside this channel, because the outside of this channel this is prohibited, and that is the way how you can confine the spin wave. Here are some kind of micromagnetic simulation I performed to show this. So basically we have a waveguide with 800 nanometer and the length 2 micrometer, and try to excite the spin wave by applying the sinusoidal magnetic field within this dotted shaded line. Okay, then interestingly you can see the spin waves are strictly confined within this channel having width 200 nanometer. Okay, but nevertheless you can also shrink the size of the channel down to 40 nanometer. Not only that, you can even change the shape of the waveguide just by the shape of the channel just by changing the shape of the top gate electrode. So the most important point is the reconfigurable properties of this channel. So basically, let's say you have a number of parallel channels, then you want to send the spin wave selectively through a channel. So you can do that. You can always do that. You can either send the spin wave with the same wave vector, or you can selectively you can select only one or a number of channels. Not only that, by applying different gate voltage, you can even tune the wave vector of the spin wave propagating through these channels. So what else you can do by this channel? Of course, you can make like magnonic crystal. So before going to magnonic crystal, I would like to introduce what are the magnonic crystal. So magnonic crystal are kind of artificial crystal which can be created when you periodically change the magnetic property of a system. For example, the arrays of magnetic dots or antidots, which are nothing but the periodically arranged holes created on a magnetic film. These are the very nice example of the magnetic crystal. So these magnetic crystals are used basically to tune the frequency versus wave vector bands of the I would say magnonic bands in this in these magnetic structures. Okay, so basically you can tune the magnonic bands, you can create the band gap, and these are very important if you want to apply this magnonic crystal for future devices. For example, if you want to build up some kind of microwave filters or attenuators and so on. So, but the problem with this static magnonic crystal, you cannot change the magnonic bands too much, because the only way to change is just by changing the orientation of the magnetic field or changing the amplitude or the magnitude of the magnetic field. So you can also create the dynamic magnonic crystal. One of the nice example is this one. So you basically make a meander shaped conductor on top of a ferromagnetic waveguide, then you send a charge current, and that essentially generates like specially non-uniform but periodic magnetic field. So effective field is periodic here. So by this way you can make a dynamic magnetic crystal. Just by changing the value of the current, you can change the magnonic band structure in a very nice manner. But can we also create the magnonic crystal by using voltage controlled magnetic anisotropy? Yes, of course you can do that. That has been shown by Professor Hillebrandt's group. So basically what you do, you periodically arrange the top gate electrode and they apply the gate voltage to tune the perpendicular anisotropy, okay, in the system. Then if you see the spin wave dispersion relation in this system, you can see at the below zone, and that is given by the inverse of the periodicity of the gate electrodes. At that below zone, the spin wave cannot propagate, I mean, in this along this waveguide. So interestingly, the width of this band gap in this system can be tuned by changing the value of the gate voltage. So here we applied the same method, so to show that this VCMA induced nano channels can be used as a magnonic crystal. So first we tried to see how the spin wave behaves in a case of only a blanket thin film, where we only change the perpendicular anisotropy by using a top gate electrode, which is made of ITO, but this is transparent. And to measure the spin wave, we use the below light scattering technique. So as you can see, when we systematically change the gate voltage, we systematically vary the spin wave frequency because the perpendicular anisotropy is changing. And here are the dispersion relation at various gate voltage. So you can see the dispersion curves are rather flat. That means the spin wave group velocity of the spin waves are quite low because this is the ultra thin film. So group velocity are quite low in this system. Now what happens if we make the channels? So in order to do that, so we made the top gate electrode like a stripe where the widths are 220 nanometer and they are separated by 220 nanometer. Then we applied the gate voltage in the system. And when we didn't apply the gate voltage, it behaves like a blanket film. So we get a single frequency, single spin wave mode. But when we applied -4 gate voltage, interestingly, this single mode is split into two spin wave mode. So if we see the dispersion relation for 0 voltage is kind of previous, it is like the previous blanket film, only a single spin wave mode. And when we applied -4 volt, you can see this mode is split into two spin wave mode 1 and mode 2, and they are separated by a band gap. So we did some kind of numerical calculation to find out what are the nature of this mode. So why two modes are generated. So you can see the mode 1 is basically is confined in the channel 1. So channel 1 is the channel outside of this gate electrode, and the high frequency mode, mode 2 is localized within the channel 2, is the channel underneath this gate electrode. So not only that, if you closely look at the mode profile, you can see something more about this. So at this wave vector, at the A point, you can see the modes are confined within this channel 1, mode 1, and mode 2 are confined within this channel 2. But when we increase the wave vector at B point, you can see the mode volume is shrinking. I mean, is more confined within the channel 1 or within the channel 1. So most probable reason behind this is the repulsion between this mode 2, which are propagating in channel 1 and channel 2. So that's why you can see this kind of very nice behavior, because below this wave vector, the spin wave dispersion for mode 1 and mode 2 are quite different, and then the dispersion character is changing, and the slope is changing. Okay, probably due to the repulsion of the spin wave propagating through channel 1 and channel 2. And the most important feature is the reconfigurable property. So basically, we measured how the band gap, this band gap, is varying as a function of gate voltage, and you can see this is you can tune the band gap starting from the 0 to about 1 gigahertz. Is just by applying the gate voltage about 6 volt. Okay, so these are the important feature of the magnonic crystal created by this voltage control magnetic anisotropy. So excuse me, how much time do I have?
A few minutes, 3-4 minutes.
Okay, sorry, I took a lot of time. So, so then I have few more slides, but I will quickly go through this. So next, I investigated the modulation of the spin wave frequency. Basically, what I did, I tried to excite the spin wave by this antenna antenna, and then by applying the gate voltage, we tried to see how much frequency we can tune of the propagating spin wave. So then directly coming to the result. So basically, I investigated the cobalt iron boron film having 3 different thickness, 1.6 nanometer, 1.8 and 2 nanometer. You can see for lower thickness of cobalt iron boron film where the perpendicular anisotropy is very close to the MS value or the demagnetizing field. So where the VCMA coefficient is much higher, so we can tune the frequency by, for example, 500 or 600 megahertz only by applying 6 volt in the system. Of course, this we cannot change this spin wave frequency much if we increase the thickness of cobalt iron boron because of the lower value of the voltage control magnetic anisotropy in this spin. So then the important study we did, the nonlinear control of the damping constant. So the controlling of the damping constant in the ferromagnetic material is very important because traditionally people use the spin transfer torque or the spin orbit torque to tune the damping or to reduce the damping in the system so that people can amplify the spin wave. People can make a spin torque nano oscillator, and in certain condition this nano oscillator can even emit the spin wave. So previously Professor Hideo Ono's group they have shown that this damping constant can be tuned by gate voltage, and that can be linearly proportional to the electric field. So that means you cannot only change the perpendicular anisotropy in the system, but you can also tune the damping constant. But the main observation in that study, I mean, they observed that the damping modulation becomes almost zero when they increase the thickness of cobalt iron boron above 1.5 nanometer, and the origin of this damping modulation was unclear at that time. So here we studied the cobalt iron boron MGO system to show the nonlinear behavior or nonlinear modulation of the damping by gate voltage is quite new, and it has never been observed before. So basically we measure the spin wave ferromagnetic resonance signal by spin pumping inverse spinel effect technique, and this is the typical inverse spinel effect signal we observe, and we fit it by this Lorentzian and anti-Lorentzian function to find out the resonance line width and the resonance speed in the system. Then we plotted the frequency as a function of the magnetic field and fitted with the Kittel formula to find out the variation of to find out the perpendicular anisotropy and its variation as a function of gate voltage. And to find out the damping constant, we plotted extracted value of half width at half maxima and the resonance line width as a function of frequency. Then by using this formula, basically what we did, we just fitted with the linear function, and then we from the slope of this fitting we extracted the damping constant by using this formula. So now coming to the result. So for thicker film, what we observe, the damping constant is linearly varying as a function of gate voltage, and as we increase the thickness, this variation becomes almost zero. And for lower thickness, instead of linear variation, we get kind of nonlinear variation. So we could nicely feed this nonlinear variation by kind of quadratic equation where the damping can be expressed as a something like this. Okay. Now, what are the origin of this nonlinear variation? So before going to that, we also I'm showing some more result measured from some kind of reference sample. So where we remove replace the the heavy material layer, the tantalum, by light metal copper, so that we do not have a loss of spin angular momentum by spin pumping. Then also we observe this nonlinear variation of damping constant, and that means we concluded that maybe the spin pumping into the heavy metal may not be solely responsible for this only the observed nonlinear behavior. Okay, and in the second scenario, what we did, we replaced the MgO layer by alumina. Okay, but in that case, we didn't see any nonlinear behavior. Then our conclusion is probably the cobalt iron boron MgO RASBA interface plays a key role for this nonlinear behavior. Now, about why this nonlinear behavior is occurring. So, because as you know, when we excite the ferromagnetic resonance in ferromagnetic thin film, it pumps pure spin current into the heavy metal. So that is the major source of losing the spin angular momentum and hence damping. So the enhancement of damping can be expressed by this where this is the spin G up and down is a spin mixing conductance. So in general, this spin mixing conductance is not affected because this is the interfacial property of the system, is not affected by the gate voltage which is applied at this interface. But there may be two possible origin of voltage dependent behavior of alpha. The first of all, the saturation magnetization, which we modulate by gate voltage, and that here is the saturation magnetization. So that can give voltage dependent behavior of the damping. And second is the spin mixing conductance of the system that may be dependent upon the gate voltage, because some part of the spin current is also pumped into this layer, and where we know the existence of RASBA spin orbit coupling. So some spins current are relaxed there, and after the spin accumulation, some of them are relaxed back. I mean, through the diffusive motion, they are relaxed back into this heavy metal. That means the total spin mixing conductance is no more independent of the gate voltage, but that can be expressed by this expression, where this gamma R is the RASBA coefficient, and that is essentially proportional, linearly proportional to the gate voltage. So if you plug in all this into this equation, you will end up this quadratic equation where alpha 0, alpha 1, alpha 2 can be expressed like this. So now talking about some of the future perspective or the challenges of the system. So basically, although I have shown some of the experimental results, but still there are a lot of things to be done. For example, the realization of the logic devices by applying VCMA still needs to be done, and then demonstration of two-dimensional magnonic crystal should be done, and the problem of the impedance mismatching should also be done in order to efficiently use the VCMA for future devices. Also, we need to increase the VCMA coefficient more than a picojoule per volt per meter. And the most important thing is the reduction of the material damping parameter, because in order to utilize VCMA, because this is interfacial effect, we need to reduce the thickness of the ferromagnetic layer, and that essentially increase the damping constant. So we need to search for a material where the damping constant is quite low, so that spin wave can propagate quite a long distance. And here are the conclusion of my talk. So, and I must acknowledge the funding agencies, 3 funding agencies which were used to utilize all this project work. And thank you very much for your kind attention. And this is the end of my talk.
Okay, thank you so much, Bivas, for this excellent lecture. On behalf of my team, Dr. Brajbhushan Singh and Mr. Pushpendra Gupta, and on behalf of all the participants, we clap for your excellent lecture. Thank you so much for giving really a variety of subtopics. So it's now open for questions, and I can see 2 long questions in the chat box. I'm reading by Pushpendra Gupta. All 3 magnonic mode can be present simultaneously. Pushpendra, do you like to ask your question, or should I read it? And the same
can you hear me, sir, now?
Yes, I can hear you.
Okay. Thank you, sir, for this excellent talk. So, sir, I have basically three questions. So, first question is these three modes which you told that magnonic modes. So, these all mode can be present simultaneously to the system, or it's like only one mode can be present in the system.
Okay.
And
So
then
here,
second,
right? Okay.
yes.
So first of all,
In your first slides, introduction part, slide number.
okay. I see. No, this is coming back to the slide, then it will be easier. Okay, it depends upon the what is the geometry in the system. For example, if you only align the magnetization in the outer plane direction, you can have only this mode, forward volume mode. And if you align the magnetization like this, perpendicular, exactly perfectly perpendicular to the wave vector, then you have this mode. But let's say, let's think about the situation that it is not the perfect case. The magnetization is aligned slightly at 45°, let's say, with the K vector, and it is aligned even a little bit of perpendicular direction. Then of course, you can have a different kind of spin wave at the same time, but their frequencies will be different. So let's say if you try to excite the spin wave with by using a microwave field having different frequency, you can only excite one spin wave at a time. But if you try to use the pulse, some kind of pulse, so that you can excite all the spin wave, of course all the spin wave will be present at the same time.
Okay, sir. So, sir, in case I am sweeping the frequency, or if I am sweeping, let's say I'm sweeping magnetic field at a particular frequency. So, is this possible that I can have more than two modes or more than one mode in a system that can be visualized by using fMR spectra?
Yes, you mean the ferromagnetic resonance? Yes, you can have, like, let's say if you fix the magnetic field, okay,
yes, sir.
The resonance condition for different modes are different. That means the frequency are different. So if you try to experimentally measure the fMR spectra, so sorry, in the fMR spectra, your question is you fix the frequency and vary the magnetic field, or either way?
Yes, sir. We fix usually frequency and then vary the magnetic field.
Okay, then you fix the frequency. Let's say, for example, you fix the frequency, I would say, at 16 gigahertz. Okay, then you can clearly see this is the resonance condition for other two modes are not satisfied unless you have the short wavelength exchange spin wave. For example, if you keep on increasing the wave vector, the dispersion relation no more looks like this. So they will be something like that. There is a quadratic term. Okay, so they will look like this. So then at some point at very high K vector, and all of them may be like they will converge. Okay, so but let's say if you want to excite study the spin wave at very low K vector, so of course you may or may not have a different spin wave depending upon the frequency you are choosing.
So, sir, is there any possibility that in case I have more than two modes in the fMR absorption spectra, how I can distinguish them, and I can say that this mode, this particular peak belongs to this mode, and second peak belongs to this mode? How I can separate and distinguish them?
Okay. First of all, the first criteria is if you know the magnetic parameter or anisotropy or magnetization of the system, you can calculate from the dispersion relation by yourself, and then you can identify. And apart from this, also there is a possibility to identify if you use relatively thicker film, let's say 20 nanometer, and you are studying the magnetostatic surface more than you are using antenna, because this is surface mode. Okay, it can go either to the top surface, propagate to the top surface of the bottom surface. So depending upon which surface you are detecting from, I mean the spin wave amplitude for opposite direction of the magnetization you are applying could be different for this mode, surface mode. But for backward volume mode, the amplitude will be same. So in that way, you can also identify. And of course, that is one, but if you use below light scattering, then of course it's much easier because you directly can measure the frequency as a function of wave vector, and from the dispersion relation you can identify.
Okay, sir. Thank you, sir.
Okay, thanks, Pushpendra. Ishita, I would like to ask your question, or should I read it? Okay, I will read Ishita's question.
Hello, sir.
Okay, please go ahead.
Okay. So thank you for such informative talk. So I had a question. So in your talk, in I think slides which are at the end of your part, so there you have shown that while increasing the voltage from 0 to -4 volt, you have generated 2 spin wave mode. So this is good from application viewpoint, but like if we continues to increase the voltage, then is it possible that the spin wave modes also will be increasing?
Okay, you mean the number of spin wave modes, right?
Yes, sir.
No, it's not possible because you have kind of 2 channels, right?
Yes.
Okay, so only one spin wave is propagating through one channel, another spin wave propagating through another channel. So if you keep on increasing the voltage, you still have a different 2 spin wave separated rather larger frequency separated by larger frequency, but you cannot increase the practically you cannot increase the voltage significantly because after some point the junction will be broken.
Okay, sir.
So yeah, that is one.
Yeah, thank you. From Somesh Kumar Sau, there is a question, just a simple question: how to understand spin pumping in a PMA sample, and how to understand ISH in a PMA sample when we have a PMA/HM layer.
Sorry, can you read one again? Probably
He's asking basically if you have a bilayer sample with a ferromagnet which has perpendicular magnetic anisotropy put next to a heavy metal, how do you explain the spin pumping?
Okay. The perpendicular anisotropy and then the magnetization is magnetization is oriented out of plane direction, and in other cases in plane direction, right?
No, there is no in plane. It's just a heavy metal ferromagnet, but the ferromagnet is having PMA.
Yes.
Then how do you explain the spin pumping and ISH?
Okay. So I go to this slide probably. So here I have shown in my case we have a perpendicular anisotropy in the system which we can modulate, but we applied the easy axis in our case was in plane of the film. Okay, because we apply the magnetic field also in plane. Then basically when we excite the ferromagnetic resonance, that carries spin angular momentum. Okay, and the pumping of the spin current basically means the transfer of the spin angular momentum to the conduction electron spin. That means the basically the up spin are going like this, or let's say down going like this, and then okay, okay, I have some echo problem. So then it is converted to the charge current by inverse spinel effect. Okay.
I hope that answers the question. So, all right. So then, thank you so much, Bivas, for this very nice talk and your time. We enjoyed it, and looking forward to meet you again in subsequent talks. So, just a small announcement: this week we will have another lecture by Professor Luis Huzo from Nanogun in Spain. So he will be giving a very nice talk on graphene related Spintronics. And then next week we will have 2 talks, one by Dr. Devanjan Bhomik from IT Delhi and Professor Albert Furt on Thursday, when we celebrate the 50th seminar. So we will celebrate the 1-year completion of W2S. So with this small note, I again thank you all. Please stay safe, and let's meet on Thursday. Thank you. Bye-bye.
Bye-bye. Thank you very much.